Hello everyone, my name is Lakita. Today I am going to make an audio recording of organic chemistry and the chapter name is Diazonium salts. Introduction. Arene diazonium salts were discovered by John Peter Grace in 1858. They have the general formula ArN2X where Ar stands for the aryl group and X may be an anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known but they are highly unstable. They rapidly decompose even at low temperature forming carbocation and nitrogen gas. Rn positive triple bond NX negative gives R positive plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic application of arene diazonium salt only, particularly with reference to benzene diazonium chloride. Nomenclature. Diazonium salts are named by adding the suffix diazonium to the name of the aromatic compound followed by the name of the anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrobenzene diazonium fluoborate, para-chlorobenzene diazonium bromide. Structure of benzene diazonium chloride. Molecular formula. The molecular formula of benzene diazonium chloride as determined from analytical data and molecular weight determination in C6H5N2Cl. Grease structure. Grease proposed structure 1 for benzene diazonium chloride in which both the nitrogen atom were directly linked to the benzene nucleons. This structure, however, failed to account for the following facts. Number 1. Its salt-like character. Number 2. Displacement of both the nitrogen atom by a univalent atom or group in most of its reaction. C6H5N2Cl gives C6H5X where X is equal to H, OH, OR, Cl, Br, I, Cn, etc. Number 3. Its reduction to phenylhydrazine in which only one nitrogen is attached to the benzene ring. C6H5N2Cl gives S in the presence of SnCl2 or Na2SO3 gives C6H5NH2 phenylhydrazine. Number 4. Formation of azo compound by coupling reaction. C6H5N2Cl plus C6H5Y gives C6H5N double bond N C6H4Y, an azo compound where Y is equal to OH or NH2. Number 5. Formation of aromatic diazonium salt from penta-substituted aniline. 2,3,5,6 tetrabromosulfonic acid in presence of NaNO2 or HCl at 273 to 278 Kelvin temperature gives 2,3,5,6 tetrabromo 4 sulfobenzene diazonium chloride. Number 3. Calculate structure. Calculate proposed structure 2 for benzene diazonium chloride in which only one nitrogen was linked to the benzene nucleus. Evidence in favor. Structure to explain most of the drawback of grease structure such as its reduction to phenylhydrazine, formation of azo compound by coupling reaction, preparation of diazonium salt from penta-substituted aniline, and displacement of both the nitrogen atom by a univalent or group. Point against calculus structure. Structure 2 cannot explain its salt-like character and its instability as compared to azo compounds since both contain N double bond N linkage. Number 4. Bloom-Strand structure. Bloom-Strand suggested structure 3 for the benzene diazonium chloride in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objection of structure 1 and 2. Structure 3 is further supported by the following facts. Number 1. Its ready solubility in water but not in common organic solvent. Number 2. Its complete ionization as shown by conductivity measurement. Number 3. The presence of a triple bond as shown by infrared spectroscopy. Number 4. Its instability as compared to azo compound. Number 5. It explains the geometrical isomerism as shown by diazoids which are the metallic salt of diazonium hydroxide. Benzene diazonium chloride in presence of NaOH gives benzene diazonium hydroxide and when reacted with NaOH gives benzene diazohydroxide or benzene diazotoic acid. The sodium benzene diazolate can exist as a pair of geometrical isomer due to hindered rotation about the N double bond N. Preparation of diazonium salts. Aromatic diazonium salt are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. ArNH2 plus NaNO2 plus 2HX in at 273 to 278 Kelvin temperature gives ArN positive triple bond NX negative arene diazonium salt plus NaX plus 2H2O. For example, C6H5NH2 plus NaNO2 plus 2HCl at 273 to 278 Kelvin temperature gives C6H5N positive NCl negative benzene diazonium chloride plus NaCl plus 2H2O. Diazonium salt are also formed when aromatic primary amine react with nitrite esters such as amyl nitrite. The nitrite ester needed for the purpose are prepared by treatment of alcohol with nitrous acid. Thus, C5H11OH plus HONO gives C5H11ONO plus H2O. C5H11ONO plus HCl plus C6H5NH2 at 273 to 278 Kelvin temperature gives C6H5N positive NCl negative plus C5H11OH plus H2O. This process of conversion of a primary aromatic amine into its diazonium salt is called diazotization. General procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. 3 moles of the acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable side reactions such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and a cold aqueous solution of sodium nitrite is added slowly to it at such a rate that the temperature of the reaction mix does not rise above 278 Kelvin. The addition of sodium nitrite solution is stopped as soon as a few drops of the reaction mixture produce a blue color with starch potassium iodide paper showing the presence of unreacted nitrous acid in the reaction mixture. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salt. The excess of nitrous acid may be destroyed by the addition of urea. NH2CONH2 urea plus 2HONO gives 2N2 plus CO2 plus 3H2O. Since diazonium salt slowly decompose even at low temperature 273 to 278 Kelvin, they are used immediately after preparation. Evidence in sport. The mechanism of diazotization of amine is supported by the observation that aromatic amine containing electron withdrawing groups such as NO2 are less easily to diazotize. This is due to the reason that the nucleophilicity of the amino group is reduced due to the electron withdrawing effect of the NO2 group as shown. Such amine can, however, be diazotized in acetic acid. Conversely, aromatic amine containing electron donating group at ortho and para position, example ortho toluidine, para anisidine, undergo diazotization much more readily than aniline. Stability of diazonium salt. Aromatic diazonium salt are much more stable than aliphatic diazonium salt due to the dispersal of positive charge over the benzene ring. Alternatively, the instability of diazonium salt is due to their tendency to eliminate an exceptionally stable molecule of the nitrogen to form carbocation. Since the phenyl or allyl carbocation is much less stable than alkyl carbocation, therefore, aromatic diazonium salt have much lower tendency to eliminate nitrogen than aliphatic diazonium salt. In other words, aromatic diazonium salt are much more stable than aliphatic diazonium salt. Physical property. Arene diazonium salt are generally colorless, crystalline solid, highly soluble in water. Many diazonium salt, especially nitrite, are dangerously explosive in the dry state. Therefore, they are never isolated but are usually prepared in situ in situ and used immediately after their preparation. However, certain diazonium salts such as fluoroborates are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complex with metallic salt such as zinc chloride, example Ar2 positive, whole twice ZnCl42 negative. These complexes are generally insoluble. Chemical properties. Arene diazonium salt are highly reactive compound. Their high reactivity arises due to excellent living ability of the diazo group as nitrogen gas N2. They are therefore certainly extremely useful synthetic reagent in organic chemistry. The reaction of diazonium salt are broadly divided into two categories. Number 1. Reaction in which the diazo group is replaced by monovalent atom or group. Number 2. Reaction in which the nitrogen atom are retained. Reaction in which the diazo group is replaced by monovalent atom or group. Some important reaction of this category along their synthetic application are discussed below. Number 1. Replacement by hydrogen deamination. The replacement of the diazo group by hydrogen or the reduction of diazonium salt to arene is usually brought about by treating a diazonium salt by hypophosphorus H3PO2 acid at room temperature, preferably in presence of Cu salt as a catalyst. Arene diazonium salt Ar2 positive X negative plus H3PO2 plus H2 in presence of Cu positive gives ARH arene plus H3PO3 phosphoric acid plus HX plus N2. This reaction can also be carried out by treating amine with sodium nitrite or hypophosphorus acid as diazing reagent. Alternatively, diazo group may be replaced by hydrogen by heating arene diazonium salt with ethanol. For example, arene diazonium salt plus CH3CH2OH on heating gives ARH arene plus N2 plus HX plus CH3CHO. This whole process involving the diazotization of an amine followed by reduction of diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salt with ethanol, two products are usually obtained. One involving the replacement of diazo group by hydrogen as discussed above and the other by the ethoxy group. Phenol benzene diazonium chloride in presence of ethanol gives benzene plus CH3CHO plus N2 plus HCl. Benzene diazonium chloride in presence of CH3CH2OH also gives phenol. The relative amount of two products, however, depend upon the nature of diazo compound and the alcohol used. If one group is present in the nucleus and ethanol is used, the replacement of diazo group by hydrogen predominate. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Benzene diazonium chloride plus CH3OH gives anisole plus N2 plus HCl. The mechanism of reaction. The reaction occurs by a free radical mechanism. Initiation. Diazonium cation plus Cu. Cu gives its electron to nitrogen and the triple bond shift toward the nitrogen gives Cu2 positive and then gives aryl radical plus N triple bond N. Synthetic application. The importance of deamination is illustrated by the following application. Number 1. Synthesis of metabromotoluene. Synthesis of metabromotoluene. Paratoluidine in presence of CH3CO whole twice O pyridine acetylation gives paramethyl acetaldehyde. Then reacted with Br2 CH3COOH called bromination gives 2-bromo-4-methyl acetaldehyde. Then reacted with 70% of H2SO4 called hydrolysis gives 2-bromo-4-methyl aniline. Reacted with NaNO2 plus HCl 273 to 278 Kelvin diazotization and then deamination takes place. The final product will be metabromotoluene. Recall, metabromotoluene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylation as bromobenzene because due to ortho-para-directing nature of methyl group and the bromine atom. Number 2. Synthesis of 1,3,5-tribromobenzene or symmetrical tribromobenzene. Aniline reacted with Br2H2O carbromination gives 2,4,6-tribromoaniline. Then diazotization takes place in presence of NaNO2HCl 273 to 278 Kelvin temperature, and after deamination 1,3,5-tribromobenzene will be formed. Synthesis of 3,5-dibromotoluene. Paratoluidine is reacted with Br2CS3COOH carbromination gives 2,6,4 2,6-dibromo-4-methylaniline, and reacted with NaNO2H2S, so 4,273 to 278 Kelvin temperature by diazotization and deamination in presence of H3PO2 Cu positive gives 3,5-dibromotoluene. Recall direct bromination of toluene with Br2 FeBr3 gives 2,4-dibromotoluene. Number 2. Replacement of hydroxyl group. Synthesis of phenol. Diazonium salt react with water in presence of Sc to form phenol. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume of boiling dilute sulfuric acid. ArN2x plus HOH H2O in presence of H2SO4 gives phenol plus N2 plus HX. The acidic condition minimize the side reaction involving the coupling of phenol with diazonium salt. Synthetic application. This reaction is especially important since only a few methods are available for the direct introduction of a hydroxyl group into the benzene nucleus. Synthesis of metanitrophenol. Metanitроaniline reacted with NaNO2H2SO4 273 to 278 Kelvin called diazotization and on boiling with dilute H2SO4 gives metanitrophenol. Number 3. Replacement by halogen. Different methods are used depending upon the type of halogen to be introduced. Number 1. Replacement by chlorine or bromine. Sandmeyer reaction. Aryl chloride and bromide can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hydrochloric acid or cuprous bromide in hydrobromic acid. This reaction called Sandmeyer reaction and gives aryl halide in 60 to 80% yield. Benzene diazonium halide ArNX negative in presence of CuBr HBr gives ArBr aryl bromide plus N2 plus X negative. Benzene diazonium halide in presence of CuCl plus HCl gives ArCl plus N2 plus X negative. For example, benzene diazonium chloride C6H5N2Cl in presence of CuCl and HCl gives C6H5Cl chlorobenzene plus N2 plus Cl negative. And benzene diazonium chloride in presence of CuBr HBr gives C6H5Br bromobenzene plus N2 plus Cl negative. It may be noted here that it is the halogen which is attached to copper which enter the nucleus. Mechanism of Sandmeyer reaction is believed to occur by a free radical pathway. Gutterman reaction. It is a modification of Sandmeyer reaction in which copper powder and a hydrogen halide nitrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Arn positive NX negative in presence of CuHBr gives ArBr and Arn2X negative in presence of CuHCl gives ArCl. Yield are often lower, around 40%, than those obtained by Sandmeyer reaction. Synthetic applications. Synthesis of 1,2,3-tribromobenzene. Paranitroaniline reacted with Br2CS3COOH bromination gives 2,6-dibromo-4-nitroaniline and reacted with NaNO2 H2SO4 273 to 278 Kelvin diazotization gives an intermediate and then reacted with CuBr HBr Sandmeyer reaction gives 3,4,5-tribromonnitrobenzene. Reacted with SnHCl and NaNO2HCl gives 3,4,5-tribromobenzene diazonium chloride. When deamination takes place, it gives 1,2,3-tribromobenzene. Replacement by iodine. The replacement of diazo group by iodine does not require cuprous halide or copper as catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or solution of iodine in potassium iodide. ArN2Cl negative plus Ki gives Ari plus N2 plus KCl, aryl iodide. Synthesis of para-iodonitrobenzene. Para-nitroaniline reacted with NaNO2 H2SO4 273 to 278 Kelvin temperature called deazotization gives an intermediate, then intermediate reacted with I2Ki gives para-iodonitrobenzene. Replacement by fluorine. Ball-Skimmer reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid HbF4, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salt, diazonium fluoroborate are fairly stable compound. When dry diazonium fluorate is heated, it decomposes to produce aryl fluoride and boron trifluoride. For example, Ar(N2) positive Cl negative plus HbF4 gives diazonium fluoroborate Ar(N2) BF4 plus HCl. Synthetic application. Synthesis of fluorobenzene. Aniline in presence of NaNO2HCl at 273 to 278 Kelvin temperature gives intermediate product and then reacted with HbF4 gives benzene diazonium fluorate. The benzene diazonium fluorate is heated, then it gives fluorobenzene plus BF3 plus N2. Replacement by a cyano group. Synthesis of nitrile. Aryl nitrile can be prepared by treating a diazonium salt with cuprous cyanide or potassium cyanide and copper powder to avoid the loss of cyanide as HCN. The diazonium salt solution is first neutralized with sodium carbonate and then treated with cuprous cyanide. Ar(N) positive X negative neutralized with Na2CO3 and CuCN or KCnCu gives aryl nitrile ArCN plus N2. This reaction is called modified Sandmeyer reaction. Synthetic application. Since hydrolysis of nitrile gives carboxylic acid, therefore synthesis of nitrile provides us with an excellent method for the preparation of carboxylic acid from nitro compound. For example, toluene in presence of HNO3H2SO4 on nitration gives para-nitrotoluene. Para-nitrotoluene reacted with FeHCl and NaOH gives para-toluidine. Then reacted with NaNO2HCl 273 to 278 Kelvin temperature and neutralized with Na2CO3. Then added CuCN, it gives para-toluonitrile. Para-toluonitrile on hydrolysis gives para-toluic acid. Number 5. Replacement by the nitro group, NO2 group. Nitro compound are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrite in presence of copper powder. Benzene diazonium chloride HbF4 in presence of HbF4 gives benzene diazonium fluoroborate and then it reacted with NaNO2Cu gives nitrobenzene plus N2 plus NaBF4. Number 6. Replacement by an arsenic acid. Arsenic acid group ASO3H2 Bart reaction. Treatment of an arene diazonium salt with sodium arsenite in presence of copper sulfate followed by acidification gives an aryl arsenic acid. For example, C6H5N positive NCl negative benzene diazonium chloride plus Na3ASO3 in presence of CuSO4 gives C6H5ASO3Na2 plus NaCl plus N2. Then it reacted with 2HCl gives phenyl arsenic acid C6H5ASO3H2 plus 2NaCl. Number 7. Replacement by an aryl group Gomberg-Bachmann reaction. When an arene diazonium salt is treated with an aromatic compound liquid or its solution in an inert solvent if solid in presence of an aqueous alkali biarylar form, yield are usually less than 40%. ArNX plus C6H6 in presence of NaOH gives ArC6H5 plus HCl plus N2. For example, para-bromodiazonium chloride plus C6H6 in presence of NaOH gives para-bromodiphenyl 35% plus N2 plus HCl. Mechanism. The reaction is believed to occur by free radical mechanism. In alkaline medium, diazonium salt are converted into the corresponding azo compound which decompose to produce aryl radical. Reaction in which nitrogen is retained. Number 1. Reduction to aryl hydrazine. Arene diazonium salt upon reduction give good yield of aryl hydrazine. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. ArN2X in presence of SnCl2, HCl, or Na2SO3 gives ArNH2 aryl hydrazine. Benzene diazonium chloride in presence of SnCl2, HCl gives phenyl hydrazine. It, however, strong reducing agents such as ZnHCl is used. The product is an aromatic amine. Benzene diazonium chloride in presence of ZnHCl gives phenyl hydrazine. Then phenyl hydrazine reacted with ZnHCl gives aniline plus ammonia NH3. Mechanism of reduction of diazonium salt with sodium sulfite. The reaction probably occurred through nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atom, forming the dianion of hydrazine sulfonic acid, when is then converted into hydrazine in presence of acid. Number 2. Coupling reaction. Arene diazonium salt react with highly reactive electron-rich aromatic compounds such as phenol and amine to form brightly colored azo compound Ar single bond N double bond and single bond Ar. This reaction is known as coupling reaction and is extensively used in azo dye industry. Whereas coupling with phenol occur in basic medium pH 9 to 10, that of amine occur in phenantly acidic medium pH 4 to 5 at 273 to 278 Kelvin. Benzene diazonium chloride plus phenol in presence of OH negative with pH N to 10, 9 to 10 at 273 to 278 Kelvin temperature gives para-hydroxy azobenzene orange color azo dye plus HCl. Benzene diazonium chloride plus aniline in presence of H positive with pH 4 to 5 at 273 to 278 Kelvin loses HCl and gives diazoaminobenzene. Then on rearrangement it gives para-aminoazobenzene of yellow color. Coupling usually occur at para position with respect to OH or the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. For example, benzene diazonium chloride plus paracresol in presence of OH negative at pH 9 to 10 gives 2-phenyl azo 4-methylphenol. If a compound contains both amino as well as hydroxyl group at para position with respect to each other, then the orientation of coupling reaction can be changed by changing the pH of medium. For example, para-aminophenol in presence of benzene diazonium chloride and OH negative pH 9 to 10 gives 4-amino 2-phenyl azophenol plus HCl. Or para-aminophenol in presence of benzene diazonium chloride and H positive at pH 4 to 5 gives 4-amino 3-phenyl azophenol plus HCl. The well-known indicator methyl orange, which is widely used in acid-base titration, is obtained by the coupling reaction of diazonium salt of sulfonyllic acid with N-dimethyl aniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenol or amine is an example of electrophilic substitution reaction in which diazonium ion act as the electrophile while phenol or amine act as the nucleophile. Number 1. Coupling with phenol. Since benzene diazonium ion are only weakly electrophilic, therefore strong nucleophile are needed for reaction to occur. Further, since phenol is weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reaction of phenol are usually carried out in alkaline medium. Role of pH. The pH of medium plays an important role in the coupling of phenol. As stated above, coupling of phenol is carried out in the weakly basic medium as explained above. In the alkaline medium, the diazonium salt first formed diazonium hydroxide, which intermediately rearranged to diazohydroxide, which further react with alkali to form the corresponding salt called the diazotate. All these three species in fact exist in equilibrium. Benzene diazonium chloride in presence of H positive gives diazonium hydroxide, and then on rearrangement it gives dihydroxide, diazohydroxide, and then in presence of NaOH gives sodium diazotate. Since at high concentration of OH negative, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, the desired coupling reaction to occur, the pH must be kept as low as possible in alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for such coupling reaction is between 9 to 10. Coupling with amine. Number 1. Tertiary amine. The mechanism of coupling of diazonium salt with tertiary amine is similar to that of phenol, except that this coupling is carried out under weakly acidic condition. Reaction with primary and secondary amine. Coupling of diazonium salt with primary or secondary amine occur in neutral or mildly alkaline medium. Here, NH2 group of the amine first attack the diazonium cation to form diazoaminobenzene. However, when the diazoaminobenzene thus formed is heated in presence of acidic medium, it undergoes diazoaminoazo rearrangement to form para-aminoazobenzene by following mechanism. Role of pH. In the presence of high concentration of H positive ion, the lone pair of electron on the nitrogen atom accept a proton. As a result, the amine exists predominantly in the protonated form. Due to the absence of a lone pair of electron on the nitrogen atom, the amine is no longer nucleophilic, and hence the coupling reaction will not occur at a same concentration of H positive ion, that is low pH, further as explained above. Too high alkalinity, high pH will also not favor coupling reaction by forming unreactive diazohydroxide or diazotate salt in significant amount. Therefore, an optimum pH of 4 to 5 is employed for such coupling reaction. Now we see the review of this chapter. Diazotization. Aromatic diazonium salt are prepared by adding a cold aqueous solution of NaNO2 to the solution or suspension of an aromatic 1 degree amine in a mineral acid HCl, H2SO4, etc. at 273 to 278 Kelvin. This reaction is called diazotization. In general, during diazotization, 1 mole of amine is treated with approx 3 mole of the mineral acid. Number 1 mole to dissolve the amine. Number 2, 1 mole to liberate HNO2 from NaNO2, and 1 mole to maintain the proper acidity of the reaction mixture to prevent the coupling of diazonium salt, thus formed with the undiazotide free amine to give the azodie. Number 3, stability. Aromatic diazonium salt are much more stable than the aliphatic diazonium salt due to dispersal of positive charge over the benzene ring. Arene diazonium salt are generally colorless crystalline solid, high soluble in water. They are stable only between 273 to 278 Kelvin. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. Number 5. Arene diazonium salt are highly reactive compound. Their reactivity arises due to excellent living ability of diazo group as N2 gas. Number 6. Substitution reaction. Diazonium salt undergo a number of substitution reaction. For example, diazo group is replaced by H by heating with H3PO2 Cu positive or with CH3CH2OH. Number 2. OH by boiling with dilute H2SO4. Number 3. Cl or Br by heating with CuClHCl, CuBr Sandmeyer reaction, or by Cu powder HCl or Cu powder HBr Gattermann reaction. Number 5. I by boiling with aqueous Ki. Number 6. Cn by heating with KCN or CuCN or KCN Cu powder. Number 7, F by treating arene diazonium salt with HbF4 followed by heating arene diazonium tetrafluoroborate, thus form Bals-Schiemann reaction. Number 8, NO2 by heating arene diazonium tetrafluoroborate with NaNO2 Cu powder, and by number 9, C6H5 by heating with C6H6NaOH Gomberg reaction. Coupling reaction. Compound containing NN group are called azo compound and are obtained by coupling arene diazonium salt either with phenol in the basic medium pH N to 10 or with amine in the acidic medium 4 to 5 pH. The well-known acid-base indicator methyl orange is prepared by coupling diazonium salt of sulfonylic acid with N dimethyl Reduction. Reduction of arene diazonium salt with SnCl2HCl with sodium sulfite Na2SO3 or sodium hydrosulfite NaHSO3 gives arene hydrazine. For example, under these conditions, benzene diazonium chloride gives phenyl hydrazine. So this is all about diazonium salt. Thank you.